Okay, let's continue. First, let's take a look at the next topic we will discuss about our EIGRP, specifically changing the metric values of routing entries. How we modify the metric values. So first, within EIGRP, at this moment, we see in this diagram we have already set up an experimental environment running EIGRP. Regarding the route entry for October 3rd, 10. 0/24 at R3, we can announce it into EIGRP. R3 can pass this route entry to its EIGRP neighbor R2. R2 can then pass this route entry to its EIGRP R1. This specific metric value has already been calculated at R1. The route entry for October 3rd, 10. 0/24 has already been learned by R1. Administrative distance 90, metric calculated as 131072. This is what R1 learned from interface 0. 0 about this route entry's metric value. So R1, from below, of course, can receive the route entry announced by R3. However, the October 3rd, 10. 0/24 route entry has a smaller administrative distance, not a smaller metric value. It is 130816. So for R1, with two same prefixes, same masks, a different route entry below, only the best route is submitted to the routing table. Eventually, the route with the smaller metric value, R1, receives the route entry directly from R3 with a smaller metric value, is submitted to the routing table. So at this moment, we go to R1's routing table. To directly see, we go to 10.10.3.0 via R3, directly as the next hop address. 1.1.13.3 students. So in the database, we show IP EIGRP topology. As we said before, in the database by default, just go show EIGRP topology. It only stores two types of route entries, successor routes and feasible successor routes. Just go show, students, then you can only see in the database table the successor routes and feasible successor routes. So, about 1.0.1, 0.3.0, we only saw one successor route. Its FD value is 130816. Next door, we R1 learned the route entry from the link above. Our own metric value to the destination, 131072. The next router, that is R2, its metric value to the destination site, 130816. Students, R1's FD is 131072. The AD below is 130816. This is our R1's path above. FD and AD, the smallest FD value. Below us is our successor route, while above, see if it meets the conditions of our feasible successor route, requiring AD value 130816 to be less than our FD value 130816. They are equal, not less than or equal to students, it's less than. So both your AD value equals my FD, then it means for R2. In fact, it cannot students. We can't do this, can't switch over. It doesn't meet our feasible successor route conditions. We haven't put it into our topology table. So how do we see all links? What should we do, right? Because, as we just mentioned, directly go show, then you can see our successor routes and feasible successor routes. So, therefore, if not met, show IP EIGRP topology. We call it all links. So, by default, you will only see successors and feasible successors. With all links, even if the conditions for feasible successor routes are not met, we can still see, for example, 10.10.3.0, the FD and AD values via R3, the FD and AD values via R2. The one with the smaller FD becomes our successor route, which is 130816, the route entry through R3, right, the AD value, because its AD equals RFD. So there is no feasible successor route. So, of course, right, the points we are discussing now, we don't need to worry too much about this parameter for now, successor and feasible successor. What we need to understand is how to change the metric values of our root entries. This is important. This is the crucial point. How to change our EIGRP route entries metric values. Root entries metric. First and foremost, the simplest way is to start with the formula, which we introduced earlier, about the formula for calculating EIGRP route entries using our K values, involving this formula in the calculation. If the default K values are 1, 0, 1, 0, 0, then we find that the formula involves only these two algorithmic parameters, the minimum bandwidth along the route and the sum of the delays divided by 10. Students, the sum of both, is actually the tunnel's width, plus the sum of delays divided by 10, multiplied by 256. This is how we calculate the metric with the formula. We can start with the formula, then in practice, or in an exam setting. Starting with the formula, we can specifically manipulate the minimum bandwidth along the route to influence our route entries' FD and AD values. For example, now standing at R1, we learn the route entry from R3 as we mentioned, according to the direction of route entry transmission. From the origin of our route entry, as we mentioned, according to the direction of transmission, from the source of our route entry, then 10 to the power of 7. What if it goes down? 10 to the power of 7, divided by the minimum bandwidth along the route. Starting from our source, Rubik's structure has 8 million kilobits per second. Then the route entry is transferred from R3 to R1. Then the route entry is sent from R3. Outward direction does not participate in our metric calculation. Inward direction at R1's interface 0. 4. Gigabit interface bandwidth, 1 million kilobits per second. Then R1 also receives the route entry, then only the minimum bandwidth. We take the minimum value between the two, 8 million and 1 million. We choose 1 million, 10 to the power of 6, plus the sum of delays. Loopback's delay, starting from the source 5000, plus the transmission direction's delay. Here, the delay is 10, 5 plus 10. So 5010 divided by 10, bracket, times 256. Then finally calculated, our metric value, 130816. So of course that means if we change the transmission direction of our route entry, the parameters on this path, of course, can be changed. Finally, this total metric value, for example, bandwidth. If we do this, I now change the bandwidth of interface 0. 3 on R1. The minimum bandwidth, currently the minimum bandwidth, is 1 million kilobits per second. I change it to 10,000 kilobits per second, from 1 million to 10,000. Students, the minimum bandwidth along the route from 10 to the power of 6, 8 million and 1 million, and 8 million and 10,000. See which is smaller. It becomes 10,010 to the power of 4, right, students? So the metric value, of course, will be affected and will change. However, this approach, we do not recommend changing all our interface bandwidths. How can that be? Changing the bandwidth to 10,000, you can indeed adjust by changing the bandwidth to achieve the adjustment of our EIGRP metric values. Now our metric value, from 10 to the power of 7, divided by 10 to the power of 4, that is 1,000 plus 501, bracket times 256. It's a bit difficult to calculate. 1501 times 256. Let's use a calculator. Then 1501 times 256 is 384256. At this moment, R1, we receive the route entry directly from R3. Metric will change to 384256. Then go show IP EIGRP topology. We directly see all links. Okay, because now our optimal successor route definitely is this upper route. Undoubtedly, because its FD value is only 131072. Below has become 384256. Then look at 10-3.0, comma. There is a successor route. FD value has become 131072. And another path, 384256. Once compared, we know FD value is definitely R2 as our optimal path. And on the other side, students, go show IP EIGRP topology. We directly look at this table. Gentlemen, discover what has appeared at this moment. We directly go show without adding all links. That is to say, at this moment in this database table, you can only see our successor roots and feasible successor roots, then R3's path. Even though your FD value is not the best, you see there is an upper path as the optimal path. But what do? The next route's metric value is less than our optimal path's FD value. The lower path becomes a feasible successor route. Meeting the conditions, once our main link, the successor route falls, our feasible successor route can immediately be submitted to the routing table, like right. Let's do an experiment. Interface 0, 0, down it. Then go show IP route, slide insert. You see the routing, all will immediately switch to. Below, the result just now down, it just popped up down log. I immediately flushed, show routing table. You see it has been submitted to the routing table. Convergence will be very fast, students. This is our EIGRP, why we need feasible successor routes, of course. This is just to give students a look at this effect. Later, we will study the query mechanism. So students should first understand this switching method. This is the first scenario, of course. It will switch back when restored. We have restored all interfaces. You see, the successor route has returned, of course. It will switch back. Definitely, the best route is submitted to the routing table. Able to be submitted definitely is the best route. Comparing FD is the smallest. But just the successor route was down. We need to be able to switch to the feasible successor route quickly, okay? It can certainly switch back. Pay attention in the routing table. In the router's routing table, we'll always only store the best route. Students will only store the best. Then compare administrative distance. Smaller administrative distance takes priority. If administrative distances are the same, compare the metric value. That was just the point. We find we can change the bandwidth method to change our device's metric value. By changing bandwidth, change the minimum bandwidth along the route. But it is not recommended. How can you take this listed minimum bandwidth changed? It's not right? A router interface of gigabit. You let it only use 10 megabits. Is that reasonable? Setting high bandwidth to use small bandwidth just to adjust the metric value. Who does that? That's too much. So I rely really so let's try to see from formula start changing bandwidth no longer works. Then delay we can move. Like now I do this. At RE here, we change the bandwidth back. No bandwidth. Now our routing all defaults back. We should again choose below 1. 1.1.3.3 as our best path. Then here show 1.0.3.0 comma hasn't switched over yet. Show IP route 1.1. 1.3.0.8.1.6. Show run interface 0. 3. I haven't changed the bandwidth back yet. Not changed back. I say change it back. Students interface 0. 3. It's best not to change such a device's bandwidth to achieve EIGRP routing. Deleted. Okay. Then I can switch back immediately. We will choose R3. 1.1.3.3 as the next hop. Then next we change the delay to realize the change of the metric value of the routing entry. Still this formula, our metric value, is still calculated by this formula, so 1.3.0.8.1.6. So from the formula, we can certainly modify our interface's delay to achieve this change in metric value. For example, now in this route, this formula, our delay bandwidth remains unchanged. Keep as is, delay we can fiddle with. From our declared route entry's source interface, our loopback 0 interface delay 5000, plus the sum of the incoming directions delay, R1's interface 0. 3 delay is 10 microseconds, so 5010 we can change, like we come to R3 here. Then loopback 0 interface itself does not need to be connected. Any device, loopback 0 interface in our work, only used for testing or for letting us establish neighbor relationships regarding the use, or rather, the selection of the route ID. Then, there's no need to connect to any data in terms of the link. Our delay is 5000 microseconds. We can adjust it, make an adjustment, for instance, interface loopback 0. We can change the delay. However, you need to be aware that when we change the delay of an interface, it is currently 5,000 microseconds. When changing it, we need to enter the value in microseconds divided by 10. You see in microseconds and then what? Also divided by 10, fellow students. For example, I want to change the delay to what? Change it to 10 microseconds. I want to change the delay to 10 microseconds. So when we want to change the delay, we need to input 10 microseconds, then divide by 10 to become 1 microsecond. Understand? Okay, sorry, not 1 microsecond. Change it to 10 seconds divided by 10, set to 1 as a unit. Now, go to show interface loopback 0. So its delay has been changed to what? Changed to 10 microseconds. Originally it was 5,000. I have now changed it to 1, which is 1/10 of 10, changed to 10 microseconds. So now, in this path for R1, what I've learned about such a 10.10.3.0 route. Its delay afterwards is no longer 5,000 plus 10, but changed to 10 microseconds, plus 10 microseconds changed to 20. Divided by 10, the formula becomes 10 plus 2 times 256. 256 times 12. Can this be done mentally? 2560 plus times 2. So we go directly to R1 to see. By changing the delay, we can also change our root metric value show, IP EIGRP topology. Then 10.10.3.0, feasible distance value. So this is achieved by starting from the formula to change the EIGRP metric values. By starting from the formula, modify along the direction of route propagation the inbound delay of the river. Right. This starts from the formula